2.1.1, properties of linear transformations. We're going to prove a few properties about them, and we're actually going to prove something where it's faster to show something as a linear transformation. So here's proposition 2.1.2. If t from v to w is a function, if we assume that t is a linear transformation, then t would send the 0 of v to the 0 of w. All right, so t preserves more than just the addition and the scalar multiplication. It preserves the 0. And then if I have a linear combination here in v, it's going to send it to a linear combination in w of the image of v1 through vn. All right, so second proposition, we get that t is linear if and only if, and we only have one property to prove, so this is a bit faster. Instead of checking that it preserves the vector, the addition and the scalar multiplication separately, we could prove it all at once. So I'm going to be able to split this and take the k out at the same step, and if I can prove I can do this, then we have the other two properties that we had before. Let me show you. Then we can prove separately that we could take k out and we could split them. And so say instead of proving two different things, you can prove a single one. All right, so for the first one, you'll prove this in a worksheet or in an assignment, and then I'm going to prove two. I'm going to prove two, so it's an if and only if. I need to prove two directions. I'm going to start by assuming that t is a transformation. Then take v1, v2, and v and k and r. We want to show that t of v1 plus k v2 is t of v1 plus kt of v2. All right, so let me start with this, but I can use the two property that we had before. So by property 2, I can split at a sum, and then by property 1, I'm going to be able to factor the t out. All right, so it's applying both properties one after the other. All right, second direction. I'm now going to assume I could split things like this, split both at once, and then I want to show that t is a linear transformation. So I'm going to need to show the two properties separately. All right, so first, I want to prove that I can factor t out. Actually, let me write it that way. So I'm going to factor t out. I'm going to write this as t of 0v plus kv. All right, so adding the 0 doesn't change the value, so these two are the same by axiom 4. But now I have something that looks like this, so I'll be able to split it. So it's going to give me t of 0v plus k t of v, and this is by star. All right, now by what you proved in here, so by 1a, that's going to give you 0 of w plus kt of v, and then 0 of w doesn't change anything, so I do get kt of v. All right, so that's property 1 proven, and then I'm going to look at property 2. I'm going to take a sum of two elements. I want to write it in this form so I could use the only hypothesis we have about t. So what I'll do is I'll write it as 1 times v2 instead of v2. Then by star, I'm going to be able to split it. All right, so here really I'm using axiom 10. So if I ask you to show all the axioms, you'd have to, but in this case, you can just use them correctly because I'm not asking you to spell out every step. And then I'm going to use star, and the 1 times tv2 by axiom 10 would be tv1 plus tv2. And so we do get the two things we want, and so T, sorry, is a linear combination. Oh, what am I saying? I just read the line after. All right, so that's not what I want. What I want is T is linear. All right, so according to property 1b above, T sends linear combination of V1, V2, Vn to a linear combination of TV1, TV2, TVn. So from this, we'll see that linear transformation works well with spans and bases. So this is going to be important because linear combination are essential to talk about dimensions, bases, linear independence, and so these kinds of maps are perfect.